Alright, welcome to Unit 4, Conservation of Energy. In this video we're starting lesson number 6, which is conservation of energy, but with some non-conservative factors going on here. In other words, that means that we are going to be having some work done to our situation. And I will briefly explain what I mean by that just before I start doing example 1, which is right now. Okay, so if you look in your books, we have a new twist to our formula. Really, it's not going to be too complicated. It's basically what we were doing in lesson 5, except we're now adding a component of work to our equations. So let me grab my marker here and say that our new formula is going to be energy mechanical before plus some work function. So this is going to be work done by some force. This F is not for friction, this is for a force, is equal to energy mechanical after. Okay, now to elaborate a little bit on what's going on, you should know work before, and if you don't, I'm not going to explain too much. Go back to lesson 1, watch the tutorials there. You'll have a pretty good concept of what work is. I'll give you a really short rundown right now. So, same situation, mechanical energy before is equal to the mechanical energy after, except some force acting on this block somewhere on its path is going to either be speeding it up or slowing it down. And by speeding it up, slowing it down, probably what's more accurate for me to say is something is going to be adding energy to it, or something's going to be taking energy away from it. An example of something that could be adding energy to this box is maybe a force applied. So if we put a force applied behind this box, force applied, it's going to add energy to this box. As it's moving, it's going to provide extra energy, which means the energy at the end won't be the same as the energy at the beginning before, because some external force is adding energy to this. That said, we can also have negative work done on our box. Forces that move in the direction opposite to motion are going to remove energy from this situation. The most likely, the most common force that is going to be moving in the opposite direction to our motion is friction. Friction, generally speaking, I want to say always, but I don't want to, say for sure without checking some facts. But work, generally speaking, is going to be removing energy from our object. It's what friction does. Okay, so energy mechanical before, plus or minus, right? We say plus in our formula, but work can be a negative value. So mechanical energy before plus or minus work function is equal to mechanical energy after. Cool. So with that said, let us take a look at this first example problem. So this example problem says to determine the average friction force, so the magnitude of friction, if its max height is 5 meters. So this block starts with some initial velocity, it's got a mass, and it's sliding up this hill. Right, this hill is 7 meters long, it's got a height of 5 meters, and it's asking us to figure out when this block comes to rest at the top, how much friction was done. So we can probably assume right off the bat that this value up top is not going to be the same as this value down here. There's going to be some difference value caused by the force of friction along the way. Okay, I think this is nicely set up. Let's jump into solving it. I've already got the first formula written up here. Mechanical energy before plus this work function is equal to the mechanical energy after. Okay, well, let's look at all of the different energies that we have for this energy mechanical before. This box, I don't know if my diagram shows it perfectly, but it is at ground level. So if there's no height value here, we can say that potential energy is out. We're not going to have any potential energy at the beginning, but we have a fairly high initial velocity. Velocity correlates to kinetic energy. So we're going to have at the beginning energy kinetic initial plus our work function. We have work function of the force of friction. So I know how I told you this F stands for just force. Well, in this case, we can change that to friction. Generally, when I do it, I don't know if I do it all the time, you can check my videos, but often I will put lowercase f when I'm referring to friction. So let's do expand out our work formula. You might want to check back at lesson 1 again if you're not comfortable with this, but our formula for work is force, so force of friction, times displacement, times cos theta, where theta is the difference in angle from the direction of our motion to the direction of our force. Alright, in this case, we have our plane moving at some angle here. I should really use a straight line tool for this. So we have our object moving like this, our motion, which I'll do with the blue tip, is this way, but our force, well, I'll use red again for force, our force is being applied backwards, which means our angle for cosine is going to be a full 180 degrees. Alright, so we're going to put a 180 degree in there when we add some numbers in. I'm not going to do that quite yet. Alright, still have red on, good. Let's do our final mechanical energy. Well, this box comes to a rest, so we know kinetic energy is out. It has a height of 5 meters, so we have potential energy, and that's all we have is potential energy. So, potential energy, final. Okay, that's our setup formula. We are solving for the force of friction here. So this is what let me switch my colors. This is what we want. Okay, let's expand this formula out a little bit here. Back to red. Okay, energy kinetic initial. So we have 1/2 mass velocity initial squared plus, again, I'll just write this out again, force of friction times delta D times cos theta. I really want to get rid of this now, but I'll save it. Is equal to mass times gravity times height. Final. Okay. Let's expand it out. Let's check which values we have and which values we need. Mass, got it. Initial velocity, got it. Alright, 2 down. Force of friction, we're solving for. Displacement, right here, 7 meters. Cos theta, this is going to be cos 180. So got it. Mass, little g. Final height. Well, look at that. We have every term already. We just need to plug them in and solve. Okay, so let's do it. I'm going to start a little bit over here because this could stretch out a little bit again. So let's do 1/2 times mass of 4 kilos times velocity of 12 meters per second squared plus force of friction times 7 meters. Yeah, this is fine with just the dots. Times cos of 180 degrees is equal to our mass again. So let's do I'll just go 4 kilos. I don't need sig digs in my, or decimals in my book if they're 0. 4 kilos times gravity 9.81 meters per second squared times the height. The height here final is 5 meters. Okay, so we can boil that down a little bit here, and I am going to skip a little bit of algebra steps and gonna go with, we end up getting, this is what I did for my next step. I solved this value, so this value works out to cos 180 is -1. So we have -7 times force of friction. -7 force of friction is equal to, and I solved both sides and then I flipped this one over and subtracted it out, and it works out to -91.8 joules. And when I do my algebra and I divide my 91.8 joules by 7, I end up getting a force of friction equivalent to 13 newtons. And that is the final answer.